Hello everyone. In this video, we're back to my IBM PC XT model 5160 motherboard from the 80s. First, we'll see if my new video card works, then we'll try to connect a modern keyboard, and then we'll see what kind of software we can run. My plan is to slowly build it into a working PC with the original parts I can get my hands on, and maybe cheating a bit to have some fun along the way. Maybe I'll even make some brand new 8-bit ISA cards. I'm sure we'll also be looking at a bit of x86 assembly programming along the way. In the first part of the video series, we diagnosed a bad power rail, fixed the BIOS ROM, and got it to post. If you'd like to know more about how we got this far, then I suggest you check out that video too. We left off where we could hear the motherboard going through the power on self-test and telling us that no video card was detected. Since then, I went on eBay and got the cheapest video card I could. I still ended up paying more than I paid for the motherboard, go figure. The card that I got for about 25 euros plus shipping is a 16-bit VGA card from the early 90s, but this specific model should also work in 8-bit mode. I've heard that it's far from all 16-bit cards that are 8-bit compatible, so it did require some homework to figure out that it probably works because other people have reported success with the same Western Digital chipset. My best guess is that this card must have been intended for the lower end of the market since the chipset itself is from '89, the card design has a '91 copyright date, and this exact board has a manufacture date of May 1992. Literally a month before PCI was introduced, to put it into perspective. The card does do 1024 by 768 as its highest resolution, but only at 16 colors or 800 by 600 at 256 colors. Certainly not a monster by any standard, but what it will do is let us plug a modern monitor into this 40-year-old design. Either way, let's plug it in and try it out. Even though we previously set the motherboard jumper settings to the monochrome display setting, we can still power it on, and for this card we'll get some output on the VGA port. But to get rid of the error code of one long beep followed by two short beeps, we will have to change the jumper settings to the EGA setting. We simply put jumper 5 and 6 to the on position instead of the off position. The actual difference is that instead of relying on the built-in BIOS display drivers, the BIOS loads a video extension from the ROM on the video card that's plugged in, which is exactly what we want since our card is a VGA card that has a ROM full of handy initialization code. I'm sure I'll be talking a lot more about BIOS extension ROMs and probably making one in a future video. But for now, let's see what happens when we power on the motherboard. It looks like the XT is successfully counting up the RAM, and I'm happy to see that since this would have been a kinda short video otherwise. We immediately get the 301 error at the top, but that's perfectly fine since 301 means the keyboard isn't detected. Now that the BIOS code has finished checking the RAM, we can move on. The 601 error means the floppy disk controller isn't detected, which also makes perfect sense. I guess we'll have to buy or make one of those if we want that error to go away, but that's certainly something for another video. So let's plug in a keyboard and get this show on the road. Okay, I don't know about you, but I don't think this is going to fit. With the IBM PC XT, the next model in the line after the XT, this isn't actually that big of a deal since it's a simple matter of rewiring the USB lines to a DIN 5 plug, and you can actually get both a passive adapter that'll convert USB to PS2 and from PS2 to DIN 5. That'll work fine as long as the keyboard supports the PS2 protocol, and many still do. So I don't have a PS2 to DIN 5 adapter, but with the XT here, we're in bigger trouble anyway. If we tried hooking it up, even using an adapter that has the correct pin out, we'll only get power to the keyboard and nothing else, since the PC and PC XT use a completely different protocol than the AT and PS2. I've heard that some keyboards in the transitional period did support both XT and PS2, but sadly my modern Philco keyboard here only supports USB and PS2. While the PS2 and AT protocols use 11 bits, the original PC and XT only use 10 bits. And many XT clones only use 9 bits, since the first is a request to send bit that can practically be ignored. Since this is an old task that's been done many times, I didn't think I'd have to dig deep to find some useful code. The first several pieces of code for converting PS2 to XT protocol turned out to be closed source or assembly language code for some obscure PIC microcontrollers that didn't survive the chip shortage particularly well. Luckily though, it didn't take too long to find something that looked pretty reasonable and was linked from several places by Kęstutis Rutkauskas, aka Kesrut on GitHub. I've made a quick schematic of my breadboard here, for those of you following along at home, that you'll find on my GitHub. I had a DIN5 connector I could solder a Cat5 cable to, so I used that, but DIN5 cables are actually still quite common and exactly the same used in MIDI cables before USB mostly took over. Let's plug it in and see what happens. It's still counting up RAM, so at least I didn't short anything, and I don't see a 301 error either, so that looks promising. While the BIOS finishes checking the RAM, we have some time to think about what happens next. As you can see, we have no other cards plugged in, no floppy drives, no hard disk, and certainly no USB to boot from, so you might expect an error like no operating system, insert disk and press any key to continue, or something like that. But if our keyboard adapter works, we'll see something that might be unexpected to some of you. Back in 1983, when the XT came out, it was unheard of to sell a computer without an operating system, and even though the intended OS was IBM PC DOS by Microsoft, it also came with 3 versions of BASIC. Disk BASIC you entered by running the DOS file basic.com, Advanced BASIC you got by running basica.com, and finally Cassette BASIC you could only enter on the XT by having neither a bootable hard disk or a floppy disk, which was rare since all XTs came with a hard drive. Lucky for us, it's part of the BIOS ROM that we fixed in part 1 of this series, which means the only thing I did to get here was press F1 to get past the floppy error. And it works! Well, at least it let me press F1, but when I just tried to enter some basic commands, it's like the keyboard is dead. The cursor is blinking, so I know it's still running, but something is certainly wrong. If we look closely, we might find the answer in the IBM Technical Reference Manual. It's really amazing to have relatively complete descriptions, circuit diagrams, and assembly source code available for everything when you try to debug the IBM XT. The downside, however, is the enormous amount of data. Just the technical reference is 422 pages, and that's only one of about half a dozen manuals of the same size for the IBM XT. By the look of it, the keyboard is expected to go through a 1 to 2 second power on reset, then do a basic assurance test, or BAT, for another 300 to 500 milliseconds, and then return hex AA to the XT computer. The keyboard should also repeat the BAT and return AA when the computer pulls the clock line low. Except for the fact that the Arduino is much faster than expected in the manual, that looks exactly like what Kesrut's code does. One thing worries me though. The manual explicitly says the keyboard's outputs are open collector, and the default state for the clock line is high. But the code we're using on the microcontroller now isn't open collector, but actually push-pull. When you connect a push-pull output pin to an open collector circuit, it's easy to get into a bad situation where the open collector side is actively pulled low, and the push-pull side is connected high. And that can certainly hurt your microcontroller, your XT, or both. What open collector means, in simplified terms, is that when the internal output transistor of the microcontroller is configured low, it's connecting the external pin to ground, but when it's high, it's essentially not connected to anything, which means you need to put an external resistor on the pin if you want it to be able to go high at all. The benefit, however, is that you can connect two separate circuits without risking a short circuit. Since if one side is high and the other pulls low, there's only a resistor to overcome and not a direct short through a transistor, letting out the magic smoke. I don't have external resistors on the breadboard for now, but the Atmega 32U4 on the Pro Micro does have some internal pull-up resistors. I read the XT keyboards usually had rather aggressive pull-ups of around 2 kilo ohms, as well as 4.7K pull-up resistors on the XT host side. That might mean our Atmega pull-ups in the 40 to 60K range won't work, or rather the 4.7K pull-ups on the host side will do all the work. Probably the short cable will also work to our advantage. Either way, we need to fix the Arduino code. Since our chip doesn't support an open collector mode, we have to use a little trick to essentially do the same thing. If, instead of driving the pin high, we flip it to an input, it'll end up in a high impedance state just like an open collector. As I mentioned a bit earlier, the micro does have internal pull-up resistors that we can enable with the input pull-up state. Some people have noticed that when the Arduino code changes from input to output, it actually drives it high for a short time. The way to avoid this is to drive the pin low before flipping it to output. Besides changing the code to make a short circuit less likely, I also noticed some confusing bit juggling where each scan code bit is put separately into an array, which didn't make sense to me, so I fixed that as well. It shouldn't physically change the output, but it's fewer lines of code and I think it's easier to read. This might be a good time to mention I am not a professional programmer, and if you try this at home, it's at your own risk. I forked the original code and added my fixes, so you can find that along with the schematic I showed earlier in my GitHub repo. You'll find a link to that in the description. I'll fast forward through the rest of the Arduino coding as it's just making the changes I already mentioned and a little bit of cleanup. If you're trying this at home, please remember to unplug the keyboard adapter while you're programming it, as otherwise you'll be running a bad amount of current through the micro and breadboard, since you'll be powering the whole XT 5V power rail through the USB port. I really hope this will work, and we are just about ready to plug the keyboard back in and power it on. I'll spare you most of the excitement of sitting through the RAM test, as the next interesting part is whether my code broke the ability to press F1, since that was the only thing it let me do before. Success! At least it still works that far. And in just a moment comes the moment of truth. But bummer. All that code writing did absolutely nothing to the problem at hand, and the system still only let us press F1. Since the code still seems to work as well as it did before, and I was hoping even better, it might be a good time to check our assumptions. Since we've already been over what the signal is supposed to look like, now might be a good time to bring out the oscilloscope and see if our expectations match reality. What we know is that for an XT, the clock is passive high and the data line is passive low, and during the reset and bat, both lines are allowed to go high unless the XT pulls them low. Since we did manage to send at least one scan code, we can't be that far off, but let's plug in the scope and see what we'll find. For now, I'm happy to see something that does look a bit like XT scan code clocks, but there's some other signal on top of it that shouldn't be there. I don't think it's power line noise, as it looks even slower than that. Half a period looks like about 55 milliseconds, so a bit under 10 Hertz. More like 9 Hertz. That 9 Hz signal kind of seems to be a reset signal from the XT, and I do see the keyboard adapter agreeing with the request and clogging out what's probably AA as soon as the clock line is released high again. That agrees perfectly with what the code is supposed to do, but it doesn't make any sense that the XT would reset the keyboard 9 times a second, when the specs for a real IBM keyboard says the bat alone should take 300 to 500 milliseconds. Luckily, my Google skills led me back to -0degrees.net, and one important sentence stood out on a page dedicated to test chamber and manufacturing test mode. The result is a square wave of about 9.1 Hz on the keyboard clock line on the motherboard's keyboard DIN connector. What was that again? 9.1 Hz on the clock pin? That's exactly what we're seeing here. That's only supposed to happen when the data line is grounded, and that doesn't even make any sense, since the data line should be grounded during normal operation, at least after the bat. I can only assume we're somehow triggering this manufacturing test mode. When I press F1, the signal continues until we enter BASIC, and at that point it looks like the clock line stays grounded. At least that explains why we can press F1 but can't enter another key when in BASIC. The XT is simply preventing the keyboard from clocking. I think we have to dig a little deeper and take a look at the post source code in the technical reference. The source code for the power-on self-test starts on page 83 in section 5 of the technical reference manual. The code is basically responsible for everything we've seen so far, and it looks like there's a cool feature to load code through the keyboard port, but I guess that's an idea for later. During post, it checks the processor registers, checks the DMA, verifies timers work to refresh DRAM, initializes interrupts, and like we see on screen, it checks RAM. And then it looks like we get to the interesting part: determine configuration and manufacturing mode. In this section, we can see the second mention of the keyboard as it calls keyboard reset, which we can assume pulls the clock line low to request a reset, and then puts the return value in the BL register. It then checks if the return value was EA, indicating an extended keyboard. If not, it checks if the value was AA, and if it was, assumes the keyboard is present, and then moves on to check the assumed 6845 chip on the MDA and CGA adapters. If it wasn't any of those values, it checks if the BL register was 65, indicating it should load the debug code from the keyboard port, and finally, if it was 0, and if so, sets the manufacturing test flag, which it would be if the data line was grounded. This tells us most of what we need to know. Since the computer has ended up in manufacturing test mode, we know the return value to the first reset wasn't AA like it was supposed to be, since that would have skipped the code enabling manufacturing test mode. Further down, we see the actual keyboard test, and that actually accounts for the fact that we don't see a 301 error, since the whole keyboard test is skipped if manufacturing test mode is enabled. The manufacturing test flag is used after the keyboard test to set up timer 0 to put the 9.1 Hz square wave on the keyboard clock. For those of you following along at home, this is on line 791 on page 90. Does that mean the whole mystery is solved? Not quite. It still doesn't explain why the first reset is returning 0 in the BL register, since that should still return AA. I was hoping the keyboard reset routine would give us the answer, but all I see the code doing is pulling the keyboard clock down for 20 milliseconds, releasing it again, and then waiting for a keyboard interrupt, which I assume occurs when a complete scan code is received, and then reading the parallel scan code from the shift register. The keyboard reset routine didn't tell me much, except that it did include a potential timeout while waiting for the scan code, so maybe that's what happened. With the original Arduino code, there would effectively be a short when the XT pulls the clock line low, and it even reads the clock line while it's still in output, so maybe that was the issue, but that doesn't explain why it wasn't fixed when we changed the code to emulate Open Collector. Either way, sometimes you just have to try things, and I figure that since the default state of the data line while in operation is low, I will give that a try. Let's hurry up and get this tiny change flashed to the micro, and let's see if that was worth a shot. It's still counting up memory without the 301 error, so I guess that either means we entered manufacturing mode again by grounding the data line, or it actually successfully sent the completion code this time. I guess we won't find out until it's time to try BASIC, so I'll speed this part up. F1 worked. And what happens if I type list? That actually worked. It's a little bit frustrating that just worked when it technically doesn't match the reference manual, but I'll take the bittersweet win because now we can actually use BASIC. I guess we'll start with the obligatory hello world. 10 question mark as a print. Hello everyone. And then 20 go to 10. Actually, I prefer it without the line change, so I'll fix line 10. To 10 question mark hello everyone. Semicolon. And let's see if that works by typing run. There we go, an IBM XT motherboard with only a VGA card and a keyboard running BASIC programs. One thing to remember about IBM BASIC is that the break key is actually Control Scroll Lock instead of Control C. That took me a bit to figure out when I tried this out in an emulator. I absolutely prefer assembly or C to BASIC, but it does get credit for being absolutely everywhere on these early home computers. The problem with this version of BASIC, though, is that it only offers one way to save your program on the XT. Since the XT repurposed the timers used for the cassette interface, and this is still just cassette BASIC, the only way to get data out is through the printer port. And since I don't have one of those yet, you'll have to wait for another time. Though I could imagine reading a parallel port print job with an Arduino. Maybe later. Before I say a little bit about what comes next in this series, I'd like to see how BASIC on the IBM XT compares to BASIC on my 6502 single-board computer. After all, my 6502 only runs at 2 MHz, so the XT at almost 5 MHz should be a lot faster, right? Of course, we can still do inline calculations like the approximation of pi using 355 divided by 113. If you've seen my previous video, you might have noticed we get an extra digits precision here compared to the version I used on the 6502. I'm not going to do extensive or very precise measurements, but at least we can check how fast both machines are at spitting out characters in BASIC. Just like in the other video, we grab a random number between 0 and 1, then we print a slash if the number is over 0.5, and otherwise we print a backslash. We could use better characters for a maze on the XT, but let's keep it the same for now. And then we just keep looping. Technically, this should give the XT an advantage since the 6502 version I used didn't support the else statement, which means another line was needed. But as you might notice, it actually looks like the puny 2 MHz 6502 is winning. That is a bit of sleight of hand though, as the screen resolution is a bit lower on the 6502 with only 50 characters versus 80 on the XT. So the XT still wins in characters per second, but you might still be surprised that it's only by a margin of around 4%, which I figured out very scientifically by pausing both screens and counting characters. Maybe the 6502 would have even won if it wasn't for the missing else keyword in the 1977 BASIC. Another test we can do is the same sine wave I did in the other video. You might think I give the XT a handicap in the first line here, but I actually just let the program run a bit longer than the 6502 version. I do, however, give the 6502 an advantage in line 20, as I kindly asked the XT to center the wave and thereby technically asking it to write twice as many characters per line. I think I need to put the next on a separate line here. But as you can see, the 6502 wins by way more than a factor of 2. Actually 4 times as fast. But before I get slaughtered in the comments, I have to point out exactly how pointless a speed comparison between 2 versions of BASIC that don't even have the same precision is. Cassette BASIC not only has an extra digit in single precision mode, it would also win by a landslide just by using the available statements to print characters and pixels at arbitrary locations on the screen. I really like playing with old stuff, but I like building stuff with old parts even more. It would probably be cheaper just to buy an old XT if the fun part was having one or programming one. But I do like drawing a line between period correctness on one side and practicality together with educational value on the other side. Many people won't feel the same, but I appreciate the convenience of going with a modern LCD screen instead of a monochrome CRT monitor. And I love that I can get to make an adapter instead of just buying a Model F keyboard. That does mean I'll sometimes be mixing old parts and new, but that certainly doesn't mean I don't appreciate an original unit restored to all its former glory, like I'm in the middle of with my IBM P70. If you've watched this far, you are definitely my target audience, and I'd appreciate it tremendously if you would leave a comment about what you liked and what I can do better. In the next part of this series, we'll take a look at this 90s network card, but not to connect to anything. Most network cards of the 90s had a socket for a ROM, and in the next part we'll take advantage of that to put some x86 assembly language code on the XT. But this has already been my longest video so far. So for now, thanks for watching.